Hey there, it's Shannon Matchick-Myers, and today we'll be covering equivalence relations for our discrete mathematics course. So let's get started. A partition of a set A is a finite or infinite collection of non-empty, mutually disjoint subsets whose union is A. So basically, non-empty means there's at least one element in there, of course, and then mutually disjoint means what? Beautiful, that all of the pairwise intersections will be equal to the empty set, okay? And actually, there's no intersection throughout the whole partition. So that's what it means. And we'll see a picture of it in our first example. Okay, so definition. Given a partition of a set A, the relation induced by the partition R is defined on A as follows. For all x and y that are elements of A, x, r, y, if and only if, there is a subset, A sub I, of the partition such that both x and y are in AI, okay? All right, so let's take a look at an example to get a feel for what's going on. This might seem a little bit strange at first, and you really have to think about sort of what's your input, what's your output kind of thing. But if we have a setup somewhat like this, notice that we have A contains the elements 0, 1, 2, 3, and 4. And then we've got 3 disjoint subsets. Do you see that there's no element from one set that is an element of the other 2 subsets, right? And I'm looking right here. Okay, so let's take a look. Let's just say that this whole thing is A, right? So we have these, different subsets. So if we call A1 equal to this subset 0, 2, A2 equal to the subset 1, subset of A, 1, and then A3 equal to the subset of A, which contains 3 and 4, right? Now, you don't have to break them up like this, but sort of to explain the big picture, I am doing so for you. So let's take a look. If we just sort of, we've got a 2 element set here, which contains 0 and 2, so we could call this one our A1, which we did. And then we've got the second subset of A2, just had the element 1 in there. And then our third one that we defined, so we called this one A2. And this one we called A3. And A3 has 3 and 4 in there. So here we go. Notice that A itself is equal to, remember this notation, the union from I equals 1 to 3 of AI, but that just equals to A1 union A2 union A3. Cool. So also note that the intersection from I equal 1 to 3 of AI is equal to A1 intersect A2 intersect A3, which is the empty set. Groovy? All right. So now just overall, we have defined A as the set of these subsets, so that we've used to partition A. So we have the subset 0, 2, which was our A1, the subset 1, so you can't just put the element 1, you have to put the subset 1, and then the subset 3, 4. And of course, A is also equal to, if you don't look at the partition, A is equal to 0, 1, 2, 3, and 4. So hopefully you can see the difference between how these things are written. This one here shows how A is partitioned, and this one here just has all of the elements of A. So in this problem here, we've been told in this example that these partitions induce a relation R on the set A, okay? So it's the partitions that are inducing this relation R on the full set A. Good so far? So all we need to do, our job here is just to find the ordered pairs that are in the relation. Starting out, what we're going to do is look at our partition set A1, which we have 0 and 2 as elements. So there's 2 elements in here. So if you take a look at 0, R2 is in there, right? Because since 0 and 2 are in this set 0, 2. Sorry. All right. What else? Beautiful. We will have 2R0, right? Again, now we've switched them. So now 2 is the x value and 0 is the y value, right? So since 2 and 0 are in the set 0, 2. But this one's the kind of tricky part. I mean, isn't it true that 0 are 0? Because 0's in there, so you can use it twice. Meaning use it one for the input and the output, the x and the y. And then what's the last one? Beautiful. 2R2, since 2 and 2 are in this partition set. Cool so far? So just from A1, what have we gotten here? We can start down here making our relation. So our relation R starting out will be 0, 0, 0, 2, 2, 0, and 2, 2. Cool so far? And just so you can keep track, right, you've got these inputs right here for your relation. These were all the inputs going along. And then you've got your kind of your outputs here. Groovy? All right, so now let's take a look at the next set. So the next set, A2, is just equal to the set containing the element 1. And so what is the only order pair in this one? Beautiful. We're going to have 1R1, since 1 and 1 are in the set containing the element 1. So we can add that one into our relation. So it comes out as an ordered pair, 1, 1. And then we have our last one. So what's going to happen? Well, for A3 equal to 3, 4, we know that 3 are 4, right? Because 3 and 4 are in the set 3, 4. We also know 4 are 3. And what are the other two? Beautiful. 3 are 3 and 4 are 4. And so the ordered pairs that we get from there will be awesome. 3, 4. Actually, I was kind of doing them in somewhat of an order. It doesn't matter. It's a set, so it doesn't matter. Let's see. You would have 3, 3, 3, 4, 4, 3, and 4, 4. Cool, cool. So that is our relation set. And remember, what is this called? It's the relation induced by this partition R. Cool, cool. So the relation induced by the partition is equal to all of these, the set of all of these ordered pairs. Groovy? All right. So, and then remember we were doing kind of directed graphs about these. So, I mean, if we did one, we'd have what? 0 through 4, right? So, 0, 1, 2, 3, and 4. And then if you kind of draw your directed graph, if we start with this one, we'd have 0, R, 0, right? We also have 0, R2. I'm going to do more curved arrows this time. And then now if we go to 1, what do we have? We had 1, 1. So I guess I didn't really do it in order. We have 1, 1 only. And then if we go to the 2s, what are we going to have for the 2s? We have 2, 0. And we have 2, 2. And then we have, that's it for the inputs of 2. And then next up, what do we have for the 3s? We have 3, 3, and then we have 3, 4. And then when we go to the 4s, what are we going to have? We're going to have 4, 3, and we're going to have 4, 4. So just a couple of things that we can look right off. I mean, do you see that, you know, this particular relation was what? It certainly was reflexive, right? Because every single input mapped to itself. Oops. So R is reflexive. And remember, those are from the circles to themselves, mapping to themselves. And then what else? Beautiful. R is reflexive, right? Because if one element maps to another, the reverse is true, right? So if the real simple way to think of it is if there's an arrow going from one number to another on the directed graph, then there's also an arrow coming back the other way. these happen to be just numbers, just integers, right? We will be looking at actual sets doing that map as well as we go on. But we do know for sure that R is symmetric. And there's no, we don't know about transitivity at this point because we just have those pairs of arrows, right? So that is it so far. So just keep that in mind. So now we get to theorem 8.3.1. So if we let A be a set with a partition and let A be the relation, oh, sorry, I thought I made all the corrections. This would be let R be the relation induced by the partition. Then R is reflexive, symmetric, and transitive. So this is a really neat theorem to have to use because as we noted here, for sure we knew that R was reflexive and symmetric, right? But now we're going to prove that it also, every relation that's induced by a partition is also going to be transitive as well as reflexive and symmetric. Cool, cool? Okay. So if you kind of are thinking about a plan, what we start with is we gotta figure out what we need for the proof. So we definitely are going to need A and its partitions, right? In your textbook, they do a finite proof. I'm going to go ahead and do an infinite proof because it works for everything. So let's get started. So the first part of the proof, remember, is a setup. And you know what? If you forget something, just maybe leave a little space because you can always go back and add something in, all right? If you forgot to identify a certain part that you find out in another area of the proof that you need. So here we go. Well, we need a sum set A, right? So let A be a set. And this is a set with a partition. Since A is a partition, we know a couple of things. We know that if we let the partition subsets we're going to denote them as A1, A2, and then ... comma, AN, and that's where you would stop if you were doing a finite proof. But we're just going to say ... since we're going to do the infinite proof. So we have a couple of things from this partition business. We know that A is going to equal to the union of all of these. So here, if we just write it out, we'd have A1 union A2 union ... union AN union ... And A1 intersect A2 intersect ... intersect AN intersect ... is equal to the empty set. Cool so far? And here we have to put something here that says whenever some subset I is not equal to J, because every set is a subset of itself, so its intersection would be all of its elements. Groovy? Okay, so what do we know from our definition? Our definition says this, that if we're given this partition, which we have, the relation induced by the partition R is defined on A as follows. For all x, r, y, all x and y in A, then x, r, y, if and only if there's a subset AI of the partition such that both x and y are in AI. So here we're going to be utilizing this definition. So why don't we write it up here? Okay. So by definition, for any x and y that belong to the set A, just restating that definition, x, r, y, if and only if, what? What was the second part of it? You can look it up. There exists a set, call it AI, right, of the partition such that what? Beautiful. X belongs to AI and Y belongs to AI. So if you know that you've got a relation induced by a partition, you know these things are true by definition. So, okay, let's get started. Now, there's going to be 3 parts because we need to show reflexivity, we need to show symmetry, and we need to show transitivity. Cool? So we'll go ahead and do them in different colors. So here we go. For part 1, so our evil plan is we need to show that for any x that belongs to A, we need to show that x also belongs to the partition AI. Cool so far? So here we go. Let's do it. Well, start out by saying let x belongs to A. So x belonging to A basically means that there has to be some partition, right, of A, some partition set of A, where x belongs to that set. So the way to say that in math is there exists an x which belongs to some AI, right? You can even write for some I. And why? Well, it's because A is equal to the union, right, of all the partitions. So A1 union, A2 union, ... union, call it AI, ... union, ... Cool? So, now where do we go? Well, there just has to exist one partition where that's true, right? So we've shown what we needed to show. So what we did here is this. We said that there's got to be a set AI, right, of the partition such that both x and y belong to AI, but x was equal to y in this particular case. So therefore, by showing that x belonged to the partition, we were able to show that the output also belonged to the partition. And thus, by definition, that proves that x are y. But in this case, it was x are x. Cool? Okay, so that one's done, and we're on to the next. So for the next one, we're showing what? Good. Symmetry. So now, what do we need to show? This one's a little bit different, right? Because we need to show for any x and y that belong to A, if x are y, then what? Y are x. So this time we're going to assume that x and y belong to A, and we're going to assume x are y. Cool? So let's set it up. We're going to let x and y belong to A, but we're going to put this condition on it, so that symbol means such that x are y. So now in the case of this proof, we're assuming this, right? And we're going to need to show this one. So now, let's do it. Since this is true, right, there exists a subset, AI, of the partition such that x belongs to AI and y belongs to AI. And again, this is by definition because that's an if and only if in the definition. Of the relation. So there exists a subset AI of the partition such that y is an element of AI and x is an element of AI. And remember, we saw that in the last example, right, that we did, that first example actually. What does that mean? By definition of R, what do we know? Beautiful. Y, R, X. Groovy? All right, so now we are looking at transitivity. So if we do our transitivity as part 3, So this time we're going to need 3 elements of A, right? So what we're going to need to show is for any x, y, and z that belong to A, if what? X, R, Y, and Y, R, Z, then X, R, Z. That's the transitivity business. So let's do it. All right? We can't assume that because that's what we're trying to prove. So here, let X, Y, and Z belong to A such that X, R, Y, and Y, R, Z. So now this one, what we're going to do is this. We're going to do this as a proof by contradiction, right? So a lot of times what happens is you say, oh, suppose that there are 2 sets such that they're not equal to each other, right? And then try to generate some kind of contradiction, all right? So let's do it. Well, we know a couple of things. We know for sure that there is some subset, call it AI, that X and Y belong to that subset because of this condition, right? So we can say there exists some AI such that X and Y are an element of AI. And the second one tells us what? There exists some other subset of the partition, call it AJ, such that Y and Z belong to AJ. Well, what we're going to do is we're going to suppose that these 2 subsets of the partition aren't equal, right? So we're going to suppose AI is not equal to AJ. We also need to say what? That AI and AJ are what? Are subsets of the partition. Good so far? I know this one's a little bit more complicated, but it's cool. Okay, well, because these guys are subsets of the partition, and if we also suppose that they are not equal to each other, what must be true? Well, if they're subsets of the partition and they're not equal to each other, then AI intersect AJ must be equal to the empty set. But looking at those sets, what do you notice? AI intersect AJ must contain Y, because it's in both of those subsets, right? So AI intersect AJ is not equal to the empty set, which is a contradiction, right? So when what have we contradicted? We've contradicted that AI wasn't equal to AJ, right? So AI must then be equal to AJ. So it follows that X and Z are elements of AI. We already knew X was, but now we know that Z is. And by definition of R, X, R, Z. And we're all done. Groovy, groovy? Okay, I know that was kind of a long one, but I thought it would be illuminating for, you know, the kinds of things that we're doing. It's good to, obviously, this would be an extreme proof to be tested on, so you wouldn't ever have this on an exam at this level. But I thought that it would increase your understanding of the topic. So here we go. Another definition. Suppose A is a set and R is an equivalence relation on A. For each element, lowercase a, in the set A, the equivalence class of A, and it's denoted like this with the brackets and the element A. And it's called the class of A for short. It's the set of all elements X that are in the set A, such that X is related to A by the relation, the equivalence relation on A. So, symbolically, we would have the class of A is equal to X belongs to A, such that X are A. And then procedurally, I mean, it's pretty similar. You would say, you could also say for any X that belongs to A, X belongs to the class of A, if and only if, remember they're powerful statements, especially when they're in a definition, if and only if X are A. Groovy? Okay, so hold on to your seats here. This one, you know, it's going to start to get a little bit crazy, but if you just follow through on these simpler examples, like this one, believe it or not, will be relatively simple, then I think you'll be fine. All right, so let's start this one out by making the directed graph, okay, of the relation. So here we've been given in this example that A, okay, we've been given in this example that this given relation R is an equivalence relation on the set A, all right? So we can utilize the definition that we went over here for this computation. So what we want to do is we want to find the distinct equivalence classes of R. So remember, if one set is equal to another set, if they're subsets of each other, right? Or you can also think of it as each set has the same elements in it. If that's true, they're equal. So we will be able to kind of reduce our answer, I guess, if you will, by finding our distinct equivalence classes. So let's do it. Our directed graph. So we have A, B, C, D. All right, so let's see what it looks like here. So for A, and all this was given in the relation. So A maps to itself, and that's it. And then B maps to itself. B also maps to D. Going to C, what do we have? C maps to itself, and that's it. And then coming back over to D, D maps to B, and D maps to itself. Okay? So this is the directed graph of the relation R. So now let's take a look at what we have going on. So this is how you have to think about it. The class of A is exactly equal to the set where X belongs to the set A such that X are A. Good so far? So, what is the only result of that? And remember, the output is just going to be the X's. And I'll highlight you to show. It's nice in this example because we do have the ordered pairs for R. Good. We're just going to get the set which contains the element A. So this is what's happening. When finding the class of A, right, we are looking at our outputs. So we're looking for the inputs that result in the output A. Good so far? And so these are all, I'm going to do all the outputs. So when we're looking at the class of A, we're looking for that second coordinate containing the element A. So when we're looking at the inputs, what do we have? Well, for this one, the only one that works is A. So we're only going to have lists of the inputs, right? So these are all the inputs. And remember, we're working with the equivalence relation on A. Good so far? Okay, so, and then that's our input. So now, let's do another one. What about the class of B? So what's that going to look like? Well, X is going to have to belong to A such that X are, beautiful, B. So let's see what we would get. So if we kind of do our little highlighting business, let's do our output first. So we're looking for all of the yellow B's, okay? So, do you see there's one here and there's one here? Cool, cool? So that means that the inputs that work are B and, D. So B and D are the results. Cool, cool? All right, so next up, what do we have? We have the class of C. So we're looking for all the inputs that belong to the set A such that that input results in an output of C. And that's going to equal 2. So now we're going to look at where the C's are as an output. And do you see there, do you see there's only one C? So the input that corresponds to that C is C. So we will get C, but you only put it once because you're just putting in the inputs. So, whoops, sorry. Input, 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 and these were our outputs. Next up, we've got one more class. Class of D is going to be equal to X belongs to A such that X R D. And that will equal to, so let's check it out. We've got outputs of D here and here, right? That I underlined in kind of the purple color. And so the inputs that correspond are going to be B and D. So B and D are the elements in the class of C. I'm sorry, are elements in the class of D. And then these here are the inputs. Groovy? All right, so what have we found? Well, we found that, isn't it true that B is equal to, the class of B is equal to the class of D? So we only have to represent that set once, okay? So here, the distinct equivalence classes of R are going to be, and I would want you to put this notation so that I knew you understood it on an exam. So we'll have the set that contains A, the set that contains B, the elements B and D, and the set that contains C. Groovy? And we're done. So, next up, we have, instead of just single elements, we've got sets as elements, all right? So let's see what we have. So I thought this would be a good practice problem for us because it'll review power sets, right? So this notation, remember, means power sets. Of X. And remember that power sets are what? All subsets of X. Good so far? So, here we go. First of all, why don't we find all of the subsets of X? So remember, how many are we going to have? I believe there was a theorem that said you're going to have 2 raised to the number of elements in the set. That's how many subsets you'll have in possible subsets in that set. So we're going to have 2 cubed subsets, which is 8 subsets. All right, so now, here we go. The power sets of X will be this set. Well, if we remember, you got to start with the empty set because the empty set is a subset of every set. And don't forget, the set itself is a subset of itself. I'll start with just the single elements. And we haven't even taken into account the relation. We're just finding all of the power sets. And then I'll go two at a time, two elements at a time. So we would have what? Beautiful. -1 and 0. -1 and 1. And then 0 and 1. So that gives us 1, 2, 3, 4, 5, 6, 7 sets. And then that last one then will be the set itself. Cool, cool? Okay. So now we need to look at this relation, all right? Equivalence relation. So R is defined on the power set of X as follows. For all sets S and T, and they're purposely smaller capitals, small capitals, in the power set of X, SRT if and only if, IFF means if and only if, the sum of the elements in S is equal to the sum of the elements in T. Cool so far? Okay, so what we are going to need to be comparing are, we want to know what the sum of the elements in the set is, because that is how our relation is. SRT if and only if. The sum of the elements in S equals the sum of the elements in T. So let's just take a look at what, if we did sum them, what would they be? So the sums, if we kind of go just to notes for ourselves. So the empty set sums to 0. This set here just sums to itself -1. The set 0 sums to 0. This set sums to 1, the set 1. The set -1 and 0 is -1, it sums to -1 plus 0, which is -1. The set -1, 1 sums to, beautiful, 0. The set 0, 1 sums to 1. And the set -1, 0, 1 sums to 0. Cool so far? All right, I'll just put sum of elements. So now we need to go through and look at these things. So let's check it out. The class of the empty set, remember, is equal to, now instead of X's, we have S's, belongs to A, such that S are the empty set. So the empty set is the output here. And so what we're really looking for is what? We're looking for all the sets that have a sum of 0 for their elements. So our inputs will be what? Wherever we see the zeros, right, that's what we're looking for. So the empty set, it has 0 elements, so we can say that sums to 0. And then what other ones? Beautiful, the set which contains the element 0. And the set which contains the elements -1 and 1. And the set that contains -1, 0, and 1. And that's all one set. So let's identify. So remember, we were looking for these outputs, right? And there's not a list of ordered pairs this time, so we just kind of trying to visualize it a bit. So the inputs are every set that summed to 0. So all of these here summed, the elements summed to 0. Cool, cool? All right, let's look at the next one. So now, the set, or the class of the set -1. Now what we're looking for is any set, any input S, set input S that belongs to the power set, the power sets of X, such that S are, well, -1 sums to -1, right? And so we're plugging in a set here instead of an element. So that's going to equal to what? Look for the -1s, right? And so I see -1s for the set -1. And then I see a -1 for the set -1, 0, meaning that these two sets sum, their elements sum to -1. Cool, cool? All right, so I'll do different colors, I guess. So we'll have, now the set -1 is the output, if you will, right? And the input, which is what we were looking for, is going to be anything that had a sum of -1. Any set whose elements sum to -1. That is what the S's were looking for. And so that was the set -1 and the set -1, 0. Groovy? All right. Let me follow up on that with the... No, I won't, because we'll have more than one that sum to 0. All right, so now we've got the class of -1. So the class of the set 0, well, 0, the sum of the elements in that set is 0. So again, we're going to be looking for things that have sets in S, the power set, that has the elements have a sum of 0. So S belongs to A such that S R and then the set of 0 equals. So now do you see it's going to be the same inputs as we had for the empty set, because those sets all sum to 0. So we'll have the empty set, the set 0, the set -1, 1, and the set -1, 0, 1. So far, the class of the empty set is equal to the class of 0. So I will go ahead and do, we were looking for zeros here. So I'll do the inputs in the same color. And sorry, I didn't close the set here. And then those were our S's. And then the output this time was the set 0. I'm going to go ahead and work a little bit more quickly so you don't get bored. You can always slow it down if you'd like. But I'm just going through and doing this set by set. Cool, cool? All right. So here we go. Enjoy. So what do we notice about some of these sets? Do you see that the class of 0 what do we see about some of these sets? Do you see that the class of the empty set is equal to the class of the set which contains the element 0, which is equal to the set that contains the elements -1 and 1, and that one's equal to, good, the set that contains -1, 0, 1. So these are all the sets whose elements sum to 0. So we only need to represent that once for the distinct, only need to represent those that set once for the distinct equivalence classes of R. And now, so we're good to go on that. And then what else do we see? That the set, which contains the element -1, is equal to the set which contains the elements of -1 and 0. So we only need to represent that one once. And then the class of, what's the other sum? When we got 1, right? So the class of 1, the set that contains the element 1, is equal to the class of the set that contains the elements 0 and 1. Cool so far? And so now we can write down what our results are, right? So the distinct equivalence classes of R are, there will be 3 sets for the distinct equivalence classes of R, right? It's going to consist of, if we pick this set here, right, which is what all of these guys equal. And then over here, if we do this set here, which these two equal to, and then we'll be doing, representing this here, which these 2 classes are equal to. And so now let's write it in. So that first set contains the empty set, the set that contains 0, the set that contains -1 and 1, and the set that contains -1, 0, and 1. And then that's our very first one. Our second set, I'm going to put them below each other so that you can see that they're each separate sets. The next set we'll write is the equivalence class of -1, all right, or the class of -1, which is equal to the class of set -1, 0. They're both sets. And that's going to be the set that contains the element -1 and the set that contains the elements -1 and 0. And then the last one will be what? The set that contains 1 and the set that contains the elements 0 and 1. So those represent the class of 1, the set 1, and the class of the set 0, 1. Groovy? All right. So we're done. I know that one was a bit complicated, but I wanted, to give you something to chew on, I guess. All right. So now the lemma 8.3.2. Suppose A is a set, R is an equivalence relation on A, and A and B are elements of A. So it turns out if A are B, then the class of A equals the class of B. Now I liked this proof because it brings back to some earlier ones where you have to show set equality. And remember, what do you need to show? We need to show that the class of A is a subset of the class of B, and the class of B is a subset of the class of A. That's how you show set equality. So now, let's set it up, okay? So let A be a set, R be an equivalence relation, on A, and why don't we suppose that A and B, those elements, belong to the set A such that A are B. So now we've got it all set up. So this is, again, kind of groovy because it brings back subsets, what it means to be a subset, and set equality and all that good stuff. So part one, we want to show what? Class of A is a subset of the class of B. And, well, what does that mean? We need to show that if X is an element of the class of A, then X is an element of the class of B. That is how we'll show that the class of A is a subset of the class of B. All right? Alrighty, let's do that. Let X belong to the class of A. So what did class mean? We wrote that like 100 million times. So X are A, and that's by definition of class. Cool so far? Well, we're assuming A are B, right, in our hypothesis. Sorry, I'm really tired. We're assuming A are B, right? So, what can we say? Since X are A and A are B, then what has to be true? Good. That means that X are B, and why can we use that? Because R is an equivalence relation. So that means what? So R is transitive. Cool, cool? Hence, X is an element of the class of B, and that tells us that the class of A is a subset of the class of B. All right, so part two calls for us to go the other way. So part two, we need to show that the class of B is a subset of the class of A. So what do we need to show? We need to show that if X is an element of the class of B, then X is an element of the class of A, is what we need to show. All right, so let's do it. Setting it up, we'll let X belong to the class of B. So XRB, and that's again by definition of class, since ARB, under our premise, remember, of our theorem, what can we do with that? BRA, and that's because R is an equivalence relation. So R is symmetric. Since XRB and BRA, it follows that what? Good. XRA. And that's because equivalence relations are transitive. So X is an element of the class of A, right, by definition of class. And thus, the class of B is a subset of the class of A. All right, so now wrapping it all up with a nice bow, we have, since the class of A is a subset of the class of B, and the class of B is a subset of the class of A, the class of A equals the class of B. Cool proof, huh? All right, so next up, we've got this lemma 8.33, where if A is a set, R is an equivalence relation on A, and A and B are elements of A, then either the class of A intersect the class of B equals the empty set, or the class of A equals the class of B. And we saw that in our last couple of examples, all right? Okay, so in this one, we're doing, I'm going to remind you of something from earlier. All right, so let's do kind of a note up top. Remember that if you have P implies, if P then Q or R, I mean, what does that mean? You're assuming P to be true, right? And so then only one of Q or R needs to be true, right? So it turns out that this is logically equivalent, and when we did our truth tables, we found this. It's logically equivalent to either P and not Q implies R, and it's also logically equivalent to P and not R implies Q. Sorry, implies Q. Okay? So if we say that, you know, I'll highlight what corresponds for P, Q, and R. So if we say that P is this statement, A is a set, R is an equivalence relation on A, and A and B are elements of A, all right? That's our premise. And then if we say that Q is the class of A intersect the class of B is the empty set, and then we're going to define R as the class of A equals the class of B. So you just pick whichever one you want to exclude, right? Meaning the Q or the R. So let's go ahead for our proof. We'll do the one where we're gonna focus on P and not R implies Q. Okay? So here we go. Proof. Let A be a set. We'll have A and B be elements of A. And R be an equivalence relation on A. We're going to suppose that the class of A intersect the class of B. When we negate that, we're just going to say it's not equal to the empty set. Cool, cool? All right. Well, since the class of A intersect the class of B is not equal to the empty set, there must exist some X that belongs to the set A such that X belongs to the class of A and X belongs to the class of B. And that is by definition of intersection. So, all right. Well, what do you think? Well, it would follow that XRA, right, and XRB, and that one is by what? By definition of class. Now let's look at the fact that R is an equivalence relation. So remember, equivalence relations are reflexive, symmetric, and transitive, right? So what can we say? We can say that ARX, what else? That's because R is symmetric. And what do we get that? Since ARX and what else do we have? XRB. What can we assume? Beautiful. ARB. That's because R is transitive. All right. Well, thus, the class of A equals the class of B from that last lemma, right? Which was lemma 8.3.2. And we're done. Okay, that was kind of a cool one. All right, so lemma 8.3.4, we're not going to prove this one, but it is available in your text. So if A is a set and R is an equivalence relation on A, then the distinct equivalence classes of R form a partition of A. So that is the union of the equivalence classes is all of A, and the intersection of any two distinct classes is empty. And again, we've seen that in those examples we worked earlier in the video. Groovy? All right, so now example 3 has another one where I wanted you to kind of remember things. So Cartesian product basically means what? So let's just take a look at, let's just kind of play around. If we had, say, let's say that we had A was 0, 1, right? The set 0, 1. And let's say B was the set 1, 2. Well, what would the Cartesian product of A and B end up being? Well, it's going to be the ordered pair 0, 1, the ordered pair 0, 2, then the ordered pair 1, 1, and the ordered pair 1, 2, all of those in a set. And the inputs all come from set A, and they're used for each of the outputs, which come from the set B, whatever's, the second part of it. Cool, cool? All right, so that's, kind of our basic Cartesian product. We'll use the official definition as part of our proof, I'm sure. But basically, we need to have a visual here, okay? So, now, if we were to take a look at the classes, right, of each of these things, what would we have? We would have all these different classes, right? So the class of 0, 1 would be what? And I'm now looking at, you know, this basis here. Well, they have to have the same y value, right? So the classes of 0, 1 are going to be the set of all of the ordered pairs that end in 1. Cool so far? So that would be 0, 1, that ordered pair, and 1, 1. Cool so far? And then the class of 0, 2 would be all of the ordered pairs that end in 2. So we would have 0, 2, and 1, 2. Good. And then do you see that the class of 1, 1 would equal to the class of 0, 1, right? Because the second coordinate in the ordered pair is 1. And the class of 1, 2 is going to equal to the class of 0, 2 for the same reason. And so now I'm using this one. We need to prove that the relation is an equivalence relation, right? So I just wanted to give you kind of an example to show you what's going on with it, and so that you can understand the proof. Okay, so to show that that a relation is an equivalence relation, remember we need to show that it is beautiful, reflexive, symmetric, and transitive. Groovy? All right, so for our proof, okay, so the reflexivity part is pretty easy because we can say Q is reflexive since each ordered pair has the same second coordinate, we'll call it. All right, and so go into symmetry. So to show that it's symmetric, basically, remember, we need to show that it maps both directions, all right? And remember that in this example, we saw that, didn't we? Remember how each of these separate classes was equal, right? And that shows you symmetry. So, but we have to do this in general now. So here, we're going to let W, X, and Y and Z be ordered pairs of real numbers such that W, X, Q, Y, Z. So that's going to follow, or it will follow that X equals Z, because that's how we defined the relation Q, right? And Z equals X, right? Because they're real numbers. So now, that we have it set up that way, what will we have? We'll have y, z, q, wx. By definition, of q, how we define q. Cool, cool. So the symmetry is done. Now we'll wrap it up with transitivity. So now we just need to get another order pair in there. So why don't we let u, the order pair u and v, w, x, and then y and z, those three order pairs, we'll let them be ordered pairs. Of real numbers. Such that uv, q, wx, and wx, q, yz. Okay, so far? Good, good. All right, so since uv, q, wx, what do we know? That means v equals x. That's by definition of q. And since wx, q, yz, we know that x equals z. And that's again by definition of q. So what do we have? Since v is x and x is z, and they're real numbers, we know what? That v is equal to z. And what will we have from v equaling z? We'll have u, v, q, y, z by definition of q, and that's going the other direction in this statement. That's starting here, right? And going here. So, hence, q is an equivalence relation. And we're done. So now we need to describe the distinct equivalence classes. So there's just going to be, as we saw again in our little scratch work to get a feel for this proof, didn't we see that basically we just have one distinct equivalence class for each real number serving as the second coordinate, right? So I'll write that in. So what that means in set notation is going to be that the distinct equivalence classes will be of the form where you've got some ordered pair x and y, right? Such that x and y belong to the real numbers and y equals b, where b is an element of the real numbers. Okay? So what that means is that you'll end up having all vertical lines in the coordinate plane. So these, all the possible equivalence classes are going to end up making up all vertical lines in the coordinate plane. Okay, so here we go. That wraps up that problem. We just have a couple definitions and a quick example. So suppose R is an equivalence relation on a set A and S is an equivalence class of R. A representative of the class S is any element A such that the class of A equals S. All right? So, another definition. Let M and N be integers and let D be a positive integer. We say that M is congruent to N modulo D, and we would write M is congruent to N mod D if and only if D divides M minus N. Or, I mean, it's pretty similar. You would say M is congruent to N mod D if and only if, D divides M minus N. So our last example has R is an equivalence relation on a set A, and we want to prove this statement here directly from the definitions of equivalence relations and equivalence class. So for all A and B and A, if the class of A equals the class of B, then A are B. All right, well, we're going to let A be a set. Rango's helping us. A and B will belong to A. And we're going to suppose that the class of A equals the class of B. All right? Well, we've been given that this is R is an equivalence relation. So what can we say? We can say since R is reflexive we know that A are A, and then from that it follows that A is an element of the class of A by definition of class. Well, since A, the class of A rather, equals the class of B, what follows from that? A would have to be an element of the class of B, and that's from the definition of set equality. Well, hence ARB, because that's by definition, of equivalence class. And we're done. All right. So I hope you have a wonderful morning, afternoon, or evening whenever you're listening to this show. And please subscribe if you like what I'm doing, and tell your friends. Bye.